Is Norbert Hegyv from Budapest. Please.
Thank you for the possibility to be here or not here just via Zoom, but it is a big pleasure for me. So the title is Consecutive Sums, Sidon sets convex sequences, old and new problems. Okay, few words about the history. So the definition sounds as follows. We have a finite or infinite sequence of integers, and the block sequence or the consecutive sequence B defined, shortly I will call it C sums as follows. It is the interval sum of the elements. So I take the elements from U to V in increasing order of the subscripts, and I collect them to the set B, A. I wrote here that also the little attention has been paid for it, but after that I made my slides, I observed that I made some surf in the internet, and I observed that it has recently become an area of renewed interest. So I'm not completely sure that that this sentence is correct here. So maybe the first or earliest result, I should say, is Gauss, who asked that add the number from 1 to 100, but he made a different way. So I should mention some earlier results. The only thing which was reasonable to consider the representation function. So I denote by RAN, which denotes the number of ways that when I can write N as a sum of consecutive elements of A. So the individual Rn is not a simple task, but the average is what reasonable or a little bit easier to calculate. The first average result is due to Levesque from 1950, who considered the simplest case, namely the A is the set of integers or sequence of integers, and he made the calculation that it is constant times log x, and the constant is exactly determined, it is 1/2. The next question or the next result is due to Leo Moser from 1963. And the next candidate, a reasonable candidate, is the consecutive primes. And he, okay, I try to move a little bit down. So he proved that for primes, this average is a constant, and the constant also determined it was the logarithm of 2. Moser made some other questions which recently are opened, namely the first sounds as follows: if there exists an integer n such that this representation function of the primes is arbitrarily large, it is conjectured that it tends to infinity as n tends to infinite. It seems to me hopeless to determine it. And the next one may be a little bit reasonable. The question sounds that is the asymptotic density of integers that can be written as a sum of consecutive primes greater than 0 or not? Okay, a very new result of an old problem of Erdős. If you consider in the Bloom web page, the number is 358, and sounds as follows: that whether there exists a set A such that every sufficiently large integer n can be represented logarithmic many times as a sum of consecutive elements. the original case, the logarithm was explicitly stated, just that it is unbounded. And recently, in the beginning of this year, Tao proved this result, namely, he constructed a set A of positive integers such that the representation function is always at least constant times log n for every sufficiently large integer. And I have to stop here a little bit. Namely, I have to mention that a high school problem that if you take the integers, the natural numbers, then if you consider the subset sums, then each integer belongs to the subset sum expected the two powers of 2. The Tau construction is a tricky one. Of course, it is a probabilistic one. And the trick here that he made a random construction after controlling the collisions of the random sets. So he collected a n node, and after some very tricky technical construction or trick is in the construction. I made some further questions. I hope so that, okay, I'm not sure that it is also an easy question. So let us take an integer k, a fixed k. And the question that, is it true that there exists a t bigger than k? So if you take the prime numbers, the consecutive prime numbers from pk up to pt, then there is a coincidence between at least two consecutive sums. Okay, here we can distinguish two cases. The first, then the lengths. Okay, so I include in the consecutive sums the singleton as well. Say the case when 2 plus 3 plus 5 plus 7 is 17, which is also a prime number. Or we take the case then the length is at least 2. Say the given problem then from 5 to 13 is the same, the sum of the consecutive elements is the same as 17 plus 19. Okay, and then a variation should be the following. If you take the gap between the consecutive prime numbers, which is denoted by dk, and we consider the sequence dn, then the previous question is answered. It is the famous celebrated theorem of Zhang, Polymath, and Maynard. Is related to the twin conjecture, twin prime conjecture. Okay, what is the simple observation? Take the SA, this is a partial sum, so take the A1 plus A2, and so on, A1 plus AI, so I is at least 1. And if I recall the definition of the consecutive sums, then a simple observation that actually the set of consecutive sums is the same than the difference of SA, more precisely the positive part of this one. So it introduced the next question of Erdős. Bloom collection, it is 357. And the question says that what is the maximum number of integers such that if we have k many elements between 1 and n, and all C sums are distinct. Okay, I should say here that they are different, but not increasing order. It was originally an Erdős-Hardsheim problem, and I found the first case when it is mentioned in a collection of Erdős-Graham monograph, which is the old and new question in old and new problems in the combinatorial number theory from 1980. Okay, and I answered this problem in 1986. Then the maximum is between 1/3 and 2/3 then, as small error, and there is no further improvement here. Okay, a very nice result of Alan Becker from 2024. It sounds that there was another question, namely that is it true that there are many C-sums between 1 and n? If you consider constant times and many, that clearly, so the number of the potential number of consecutive sums is n over 2 plus n, if we consider the singletons as well. And Becker proved that it is allowed. So he constructs k-many elements between an increasing sequence of integers between 1 and n, such that there are at least constant times n squared. So what it is the maximum, not more are expected. Distinct integers of the form in consecutive sums. Interestingly, he gave both probabilistic and deterministic constructions as well. Return back to the base formula, namely that the consecutive sums is actually the difference set of the partial sum set. I mean that the positive parts. These problems belong to the Sidon problems. And so the previous result is related as well. Okay, so here, if you take that the elements of the consecutive elements of A is a strictly increasing function, then is clearly that the partial sum, so SA is a convex set. Convex set means, or convex sequence means, that the consecutive differences increases, so at least as the previous one. So therefore, it's reasonable introduce the convex Sidon sets, but before to mention it, I mentioned another question, namely the translating problem. It was also a question of Erdős. So denoted by T, it depends on the set A and the length of the sequence A, the minimal value of T for which if we translate the sequence, then the C-sums are pairwise different. It is not too hard that for every finite sequence A, this function exists. And I proved also in 1986 that in the simplest case, then A is the set from 1 to k, then this translation number lies between k squared over 25 and k squared over 4. And the next one what I should mention is the question of Erdős. In 1984, he asked me the following question, that let A1, A2, and so on, AN, and so on, so an infinite sequence, be a strictly increasing sequence of positive integers, the starting elements denoted by A, and the restriction that the difference of the consecutive element, of the neighbors elements, is bounded by K. So it means that A2 is at most A plus K, and so on. The question of him was that if all C-sums distinct, that what is the maximum possible value of the last element A? So very reasonable to believe that it would be not an infinite sequence where all C-sums are pairwise different. And I gave an upper bound for it, namely that if we denote it by FAK, the maximum integer for it, then this function is an upper bound for this one. And after a little bit later and more, so when I prepared myself, I considered again and some elementary calculus, some modification, one can obtain a little bit better estimation, but remains an exponential one. Unfortunately, there is no improvement, big improvement. I asked about tau, and he said that there is no reasonable attack for this one. But the interesting fact about it, that let us consider that k is 1. And because it is an increasing, it means that it is the sequence of consecutive element of the integers, so n plus 1, and so on. So therefore, we can have a corollary of it, namely for the translating theorem. So when the difference is 1 and the starting element is a, then we ask that what is the farthest element when we have pairwise different consecutive sums. And the result is what you see, that it is a plus 2 times square root a and a plus more or less 5 times square root of a. And interestingly, recently Garayev and Kondyagin proved the following. Sergei mentioned in Tuesday this result, namely the following one. So given a big integer n and consider the squares between n and n plus square root of a n plus something, that it is a Sidon set. And it is interesting and exciting thing because there is a connection, this problem and the translative problem. And I calculated and I observed that from this theorem, one can calculate the same bound as I obtained later. So I should mention here an important thing, that Peter Pach and Kuan-Yu Tang have a progress obtaining non-trivial lower bounds for f of a k. Unfortunately, it is not exponential. Okay, so I turn to the question of convex Sidon sets. So my request is that we have a Sidon set which is convex, and the question that what can we say about it? The trivial example is the power of 2, which is clearly a convex Sidon set, and the next one, what what about polynomial? Then n squared and n cubed and to the 4 are not, and it has a simple arithmetic reason. And an old question is that what about the fifth power? There is no progress. It's just what Ruja made in 2001. He made a little bit more general result, namely that we have parameters alpha and beta, and alpha is bigger than 4, beta is less than a and bigger than what you see here. And take the fn, which is the integer part of n to the alpha, plus c times n to the beta, and the statement of him that for almost alpha, which belongs to the interval 0, 1, there is a threshold depending on the parameters such that this set is a Sidon set. So if you take, instead of n to the alpha, so not a polynomial, just a power, and if it is, you can consider that a polynomial, that he obtained almost the fifth power, just some error here. and this condition can be written here. So define the generalized polynomials. It is the function of, so it is made from polynomials using the floor function and the fractional function, say square root x and so on. What you see are generalized polynomials, and it is not too hard to see the following proposition that what are the generalized polynomial with degree 2. That it is just a okay, so just count all possibilities, n squared and so on. And I proved that there is no generalized polynomial with degree 2, which is a Sidon sequence. And the proof is based on the reformulation of the bound, what I mentioned here before. It was the question of Erdős. So if you take this upper bound, then the reformulation sounds as follows. If A is a convex Sidon sequence of length n, then the maximum second difference is bounded below by a logarithm function. And if you consider the second what is it? Okay. Second differences. Okay, let us say the second differences. If you take second differences here, that clearly it will be just a constant which depends on the constants. Okay, a little bit more. So if instead of a polynomial, we consider a relaxation, if we relax the fact that we have polynomials, second degree polynomials, like in Ruzhan, we obtain a little bit more. Okay, and finally, I mentioned the reconstruction problems or inverse question. It sounds as follows, that if we have a finite sequence of increasing integers and someone give us the consecutive sums in ordered form, except the singletons, so we omit from it. So there is a list of consecutive sums, which the length of it is at least 2, and it is given. Then the proposition sounds that if it is given this modified consecutive sums, then there is an algorithmic running time at most n plus 1 over 2 plus 1, which determines the sequence A. And finally, I mentioned some generalization. Instead of all consecutive sums, let us bound the number of elements. And this next one, that we have an alphabet, so 1, 2, 3, say, and we consider as a sequence of this sequence, that again we ask that what is the length, what is the maximum length of this one when the consecutive sums are pairwise different. And finally, in higher dimension, okay, what would be the consecutive sense? That we can perform as follows, that we have an n times m matrix, and we consider block sums or B sums when it is an H times W rectangle submatrices. Then so we omit again the trivial 1 times 1 cells. And the theorem is the following. There is an n times m matrix when the entry is bounded by, the absolute value is bounded by m. Then there is a translation matrix. It is resembles to the integer case. Then if someone gives the B sums of m plus t, of course, omitting the 1 times 1 cells, then there is an algorithm which uniquely determines the entries. And here is actually shortly the strategy. Without loss of generality, we can assume that it is a 3 to the k times 3 to the k matrix. And after we divide by 9 many 3 to the k minus 1 times 3 to the k minus 1 blocks, And the translation, then the role of the translation is that we can distinguish, say, the two times one blocks. So okay, so up it is increasing, and to right also increasing. So what is the trick? Here is given the biggest one, and after it will be the next one because it is bigger than this one. So these two blocks can be distinguished, and we add this one and obtain the left down, the lowest block of determined. And the remaining block can be directly computed by exploring the properties of translation n. So if it is given, then there is a block sum which is given here. It is you can find it because it is the role of the translation matrix, and recursively, if they are given, that we repeat the previous process. Thank you for your attention.
Thank you, Norbert. Are there any questions for our speaker?
Okay. Okay. Stop share. Okay.
Thank you, Norbert. We now have a 1 hour break for lunch.
Give a better answer to your question. It's easier to construct something that will cover all the integers